Hi, my name is Shannon Davis. I'm a principal AI security researcher from Foundation AI and Surge here at Cisco. Today I'm going to run you through my latest project called PLoB, which stands for Post-Logon Behavior Fingerprinting and Detection. I'm excited to be using one of our very own security models from Foundation AI in this project, and I'll be covering more about that later in the video. The problem I set about tackling in PLoB was the use of compromised credentials by adversaries. As you can see here in Verizon's 2025 DBIR report, nearly one-third of all incidents they responded to in the year prior involved the use of compromised credentials, making it one of the most used techniques in breaches. PLoB has three key tenets: the use of standard logs, fingerprinting user behavior in a rapid manner, and then using a combination of anomaly detection and LLM contextual analysis to find bad behavior. I created that allows an analyst to interact with the setup. This notebook can also sit behind the scenes to work autonomously in a production environment. The diagram outlines the various components of PLoB, which are a Splunk backend for log collection, a Neo4j graph database that allows us to represent the user sessions in a way that they have actually transpired, an embedding model that allows us to create vector representations of the sessions to then store in a Milvus vector database, and finally, our two LLM models from Foundation AI and OpenAI that work together to help contextualize what is most likely going on in the anomalous sessions. Some of these notebook cells we'll dive deeper into where it makes sense. Some of them are basic environment preparation cells that just get things ready for PLoB to work. As mentioned earlier, we're using Splunk to collect our log data. PLoB was initially built to detect compromised credentials in Windows environments, but the view is that it can be expanded out to other use cases where users log on to something and then perform subsequent actions. We take two different event types: successful Windows logons, which are event code 4624, and process execution events, which are event code 4688. Preferably, we also want command line execution data as well for more granular anomaly detection capabilities. The search I'm using is on the right to correlate these two together and output the required data to PLoB. We can see the data being ingested over a 48-hour search window from Splunk here. We make sure that the data is in the format and type that we need before moving on. The next step is where we build historical baselines for processes and command line executions. We are doing this for each user host pair, and across the entire organization. This allows us to capture both distinct and pervasive behaviors that we'll use in later steps. We now populate our Neo4j graph database with the combined logon and process execution data. A session within Neo4j looks like this. We have a user who's logged onto a host, which then spawned a session that then initiates one or more processes, which could then have further child or grandchild processes. We use this for multiple steps in PLoB, but one of the most powerful ones is something I'll share at the very end of this video. At the heart of PLoB is our fingerprinting algorithm. This fingerprint allows us to understand what is normal and what is an anomaly. I'm not saying anything about good versus bad here, as we don't know that until later. At a high level, the fingerprint is made up of the executables and the commands a user ran. The process fanout, which is how many child processes any particular process spawned. The process tree depth, which is how deep a particular process chain got. For example, a process that spawned a child process, which then spawned a grandchild process, would have a process tree depth of 3. We take our baselines from earlier to see if things are close to the same or very different from the norms, and then we also look at process execution timing to see if a user is firing off processes faster or slower than usual. We embed this text fingerprint as a vector in our Milvus database using the text embedding 3 large model from OpenAI. Now that we've inserted our vectorized fingerprints, we can then perform distance calculations against all other fingerprints in our vector database. We're using a cosine distance function to determine if a session falls within 2 categories. The first is an outlier. The pink or top left circle for our color impaired friends is far away from the other 2 clusters, making that session an outlier. The other category is clusters. The 3 pink or left side cluster is much tighter packed than the others. This could be a sign of an automated script or bot doing something in your environment that it shouldn't be. If we've determined that any of the sessions are outliers or clusters, we then make use of our 2 LLMs to help provide risk scoring and contextual analysis across the raw session data. We take the data from our Neo4j graph database, send it to both the Foundation AI and OpenAI LLMs, which will then return their findings. These findings are then cross-referenced to the alternate LLM for it to judge the results from its counterpart. All of this data is then returned to the analyst to make a final judgment call. You can see in my notebook the LLMs doing their thing with my anomalous sessions here. The first session is a real malicious session that I created in my dataset, and both OpenAI and Foundation AI models are ranking that as a risk score of 6, while the other benign session is ranked as a 5 by OpenAI and a 4 by Foundation AI. They then rate each other's responses with some feedback, which could potentially be used to help tune the models or even the prompts used when interacting with the models. This sort of analysis can result in much faster and more accurate analysis by the analyst, who would have had to piece all of this information together manually in the past. The final step provides the analyst with a powerful visual representation of the malicious session. I'm taking the session ID for that higher risk session and passing that through to help craft a session graph here. You can see the user who logged onto the host, which then created the session, along with the malicious activity that ultimately led to the higher risk score. Thanks for watching this video. PLoB will have continued development across different data types and further model refinement moving forward. So if you have any suggestions or critiques, I'd be happy to hear them. Thanks.